G'day, I'm James, and I'm a math guy. For some while now, I've been actually helping to do my bit to think deeply about a K-12 college-level mathematics curriculum. Particularly recently, I've been bringing together all my thoughts and ponderings and writings on arithmetic and algebra as they span those years of education. And as I've been doing that, I've been using three principles to help guide me. But these principles are often overlooked, and maybe not even recognized as principles, but I actually think they're kind of important. So I thought I might share them with you today. It is absolutely appropriate to give students a concrete base to motivate a new topic in mathematics and to give them something solid to hold on to. In fact, so much of mathematics is motivated by real-world setups and is particularly good at describing real-world scenarios and making predictions from them and about them. Grand and good. But here's a paradox. Mathematics actually sits at a higher plane to real-world models, and no one model can actually give the full story that mathematics is used to describe it and motivate it. It's kind of paradoxical. And the curriculum suffers from this paradox. In particular, the story of fractions. It's all based on different models. We're trying to describe mathematics from different real-world models, but no one model works. It becomes a very confusing picture to students. Multiplication is another one. What is multiplication? We keep trying to give different real-world models of multiplication to explain what it is, and each model fails. They're very deep issues, those two in particular. But I don't have time to go into those ones, but let me give you another particular example that shows a real-world model can motivate a piece of mathematics, but fail to fully describe it, and what we can do about it. Okay, let me give a very speedy lesson on exponents. We'll talk about powers right now. And my real-world model to motivate us is a strip of paper. Here it is. So here's a strip of paper, and what I'm going to do is fold it in half. In fact, if I give it one fold, pick up the right end, fold it over the left end, I can see I get 2 layers of paper. So one fold of a strip of paper gives me 2 layers. All right, let me do a second fold. Always right from left. Here goes. There we go. I'm going to double the number of layers, and now I have 4 layers. 2 folds gives me 4 layers. I took my previous answer and doubled it. 4 is really 2 times 2. Here comes a third fold. How many layers do I get? Well, I'll double those 4 and now make it 8 layers. 3 folds gives me 8 layers, which is really 2 times 2 times 2. And if I was doing yet another fold, a fourth one, I'll get 16 layers, which is really 2 times 2 times 2 times 2. All right, I can see right now I'm doing repeated multiplication for my paper folding. And it gets very tedious to write out 2 times 2 times 2 times 2 4 times. People have a notation for that. They write 2 to a superscript 4. Multiply the number 2 by itself 4 times. This will be 2 to the third power, multiply 2 by itself 3 times. This will be 2 to the second power, multiply 2 by itself 2 times. This one's a bit weird. Multiply 2 by itself 1 time. It's a little bit shaky there, but I can go with that one. I can go with that. Great. So I've just introduced exponents, and I can play with a nice whole number of exponents here and have lots of mathematics fun with that. But at some point I want to see if I can push my mathematics even further. For example, these are nice whole positive numbers. Could I actually start talking about exponents for different types of numbers, like 0. What's 2 to the 0? If I did 0 folds, how many layers of paper would I have? Do you know what? The paper model is going to be great for this. I can do it. Here goes. Watch me. I'm about to do 0 folds. Watching, watching, watch. There it is. I did no folds. And how many layers do I have? I've got my 1 layer. 2 to the 0 must be 1, according to this paper model. All right. Well, let's get kind of more curious here. What if I did -1 folds? What is that if I want to, that is, what if I want to ask for 2 to the -1, according to this model? Now, I'm really pushing my physical model here, but I say, okay, I want to do -1 folds. I want to do the opposite of a fold. I want to do an anti-fold. Well, fold is going up and over this way. So what's the opposite of going up from the right over to the left? It must be doing, well, literally the opposite of that. Imagine I could peel this paper from the right, peel it, and then get something like this, twice as long, but half as thick. According to my paper folding model, 2 to the -1 will give me half a layer. If I peel it apart, I get half a layer. If I did 2 to the -2, there's 2 anti-folds. Peel once, and then peel again. I can see I'm going to get something pretty long, but it's going to be 1/4 of a layer thick. Whoa, this paper model is fabulous and good. I'm getting actually an understanding of all sorts of powers now. This is great, beyond the obvious physical ones. All right, I love this model. I can do great mathematics with that. I can see lots of patterns going on. Looks like I'm dividing by 2, 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 dividing by 2. It all fits beautifully. But let's keep going, because I now want to actually say, all right, let's push this mathematics even further. For example, what if I did something between 0 and 1? What if I wanted half a fold, 2 to the half? What is 2 to the half? And I say to myself, okay, what is half a fold? Okay, so half a fold could be, well, instead of going 180 degrees over to make a full fold, I guess half a fold is what, just 90 degrees? How many layers is that? No idea, no idea. Or maybe half a fold means go fold halfway across and get, I don't know, something that's like 1 layer thick and 2 layers thick. So maybe the average is 1.5 layers, maybe 2.5 is 1.5. Okay, now we're pushing the mathematics beyond the model. The model is now breaking down for us, it's not helping. We have to say goodbye to the model. Because now we have to rely on the mathematics. This paper folding model goes so far, but it breaks down. All models will eventually break down. So the question is, how can I handle something like 2 to the half? Well, it's got to be about the mathematics itself. What's the mathematics going on here? What's the true core math at play here? And the thing to realize is that exponents in this case are really about repeated multiplication. It's about multiplication. So it's natural to ask, okay, how does the exponents, powers, play with multiplication? For example, if I did 2 squared times 2 cubed, well, in my mind I can see it's 2 times 2 times 2 times 2 times 2. That's actually a product of 5 2's. It's 2 to the 5th. In general, 2 to the a times 2 to the b is 2 to the a plus b. That seems to be the core mathematics at play behind exponents. Now, what's lovely about the core mathematics, because it goes beyond the paper model itself. It explains the model in some sense and goes beyond it. For example, I was a little bit nervous about 2 to the 0, but let me do it. According to this core piece of mathematics, 2 to the 0 times 2 to the 3 will be 2 to the 0 plus 3. All right, I know what 2 to the 3 is. It's 8. Something times 8 equals 8. No choice. That has to be 1. Bingo. There it is. Or if I want to play 2 to the negative 1, I can do the same game. Let's play with the core piece of mathematics. 2 to the negative 1 times 2 to the 3 would have to be 2 to the negative 1 plus 3, which is 2 to the 2. I know that number, it's 4. I know this number, it's 8. Something times 8 equals 4. No choice, that has to be a half. Beautiful, beautiful, beautiful. And then now we can do the funky one, 2 to the 1/2. And it takes some inspiration to realize the way to handle that one, according to the mathematics, is multiply it by itself. Then I'll get 2 to the half times 2 to the half is 2 to the 1, and 2 to the 1 is, 2 to the 1 is 2. Something times itself equals 2. We call that the square root of 2, which is about 1.414. So apparently folding a piece of paper in half a time gives you 1.414 layers. Nonsense, meaningless. Of course it's meaningless because we actually now let the mathematics take us beyond the physical model. No one model will explain all the mathematics. Here's a lovely example of that right there. Okay, here's a task. Please sketch a graph of this beastly looking thing, this polynomial equation right here. Whoa, whoa, okay, this looks really scary. In fact, actually, let me explain something right now. There are 2 fundamental steps in problem solving that no one ever seems to talk about, and I've just exhibited the first one. Step 1, be your honest human self and acknowledge your human reaction. I said this looks scary because I am actually scared. I'm a human being that looks at this and is scared. I'm acknowledging my humanness, and that's fine. I am scared, I'm nervous. Step 2, just hope you do it right then. Take a deep breath, and then see if you can do something. Do anything. If we can teach the world just to do something, any step of any size, to get over an emotional impasse, what a gift to the world that is. And mathematics is a beautiful vehicle for teaching how to move past emotional impasses. So the question is, can I do something, just anything, anything? Well, I'm asked to sketch the graph. I could actually just draw some axes. There's something, and I'm proud of myself because I've just done something. I can even label them X and Y. Great, I've just done something. Great, great, great. Okay, is there a next something I can do? And I look at this and see, well, actually, there's some numbers staring me in the face. 30, 4, 2, and 40. There's some exponents as well, but they seem to be the key numbers because I can see, I can see right now, if I say x is actually 30, this will be 30 minus 30. That's 0 to the 6th power. That's all 0 times stuff. So when x is 30, y will be 0. There's a data point right on the x-axis there. At x equals 30, y equals 0. In fact, at x equals 4, y is going to be 0. There's a second data point. I'm plotting data points. I'm actually starting to sketch the graph. This is awesome. When x is negative 2, it's going to be 0. And when x is negative 40, it's going to be 0. Bingo, I've got some data points for my graph. Great. Actually, I can argue it's not going to be 0 anywhere else. For example, a number like, 17, I can see not 0, not 0, not 0, not 0. It's not, in fact, it's not going to be 0 anywhere else. So it's the only place it crosses the x-axis. All right. Well, that was really nice. Okay, well, there are nice x values staring me in the face. Are there any other x values that stare me in the face? Not really, except I often like to go to extremes. For example, doing a number like 10 billion, positive 10 billion, way out here, what sort of answer will come out? Well, if this is a big positive number, 10 billion take away 30 is big positive raised to a 68th power is going to be huge and positive. 10 billion take away 4 raised to the 37th power, huge and positive. 10 billion plus 2 raised up is going to be huge and positive. 10 billion plus 40 raised up is going to be really huge and positive. Positive and positive and positive and positive. I can see this thing wants to blow up and become ridiculously large and positive as I go out to huge and positive inputs. Great! All right, other extreme, like negative 10 billion. What happens? Put in negative 10 billion to an even power. Oh, shouldn't erase it, because anything to an even power is going to be positive. Negative 10 billion take away 4, a big negative number to an odd power would be huge and negative. 10 billion, negative 10 billion plus 2, huge and negative to an odd power would be negative. Negative 10 billion plus 40, huge and negative to an even power, still positive. So at negative 10 billion, this extreme, positive times negative times positive, is going to be huge and positive as well. This is great. This is great. In fact, now I can see it's never going to be 0 again. It has to get to be 0 here. So I can know the graph has to do what it's going to do, go down to 0 there. And I can just see even now it's going like to 0 there. This graph is coming together. Well, I don't know right now what's happening in between these sections where it's 0. Well, maybe it's always positive, maybe it's always negative, but it will never cross again. It's either always positive or always negative. Common sense tells me it's positive or negative. How do I know which? I know, I'll put in negative 30. Put in negative 30, I'll get negative 60 to an even power, positive. Negative 34 to an odd power, negative. Negative 30 is negative 28 to an odd power, negative. Negative 30 is an even number to an even power, positive. Great, it's going to be this, it's going to be positive, negative, negative, positive, it's going to be positive. So it's going to be positive all through here. I don't know what it's doing in between, but there it is. The best I can draw given the knowledge I have right now. Twixt negative 2 and 4. I'll try 0, because I know it's going to be all positive, all negative, it'll never cross the nexus. Try 0, that'll be, in fact, anything to an even power is always going to be positive. That's always going to be positive. These ones are the interesting ones. If I put in 0, I'll get negative 4 to an odd, that's negative. Put in 0, I'll get positive 2 to an odd, that's positive. I can see the whole thing's going to be negative over here. Whoa, great. And finally, I'll do something like 20, positive, positive, positive and positive. It's going to be positive all through there. Great, great, great. And there is a graph. I've done it. All I did there was follow my nose, use my common sense, my instincts, and just be confident about my common sense and my instincts. And there it is, it fell into place. Beautiful. It's stunning. That's what we should be teaching the world, the confidence to use your common sense. We do so much scaffolding in the curriculum. It's like we keep doing stuff, do these small steps because you need to know them later on. The human brain does not work that way. Start with something scary. Have the emotional reaction, because that's the life lesson. And then you realize you can actually use your common sense to work your way through it. Now, students will notice things like the even powers are particularly nice. They're always going to be positive no matter what. That's grand and good. Odd powers are the ones that really trying to actually determine the behavior. You'll start to realize that. You know, I know we can teach kids that this 30, whatever it is that an even power is going to corresponds to a bounce, and odd powers corresponds to a cross through. You don't need that. They'll come out naturally. Some students might even notice it. Great, let them notice it. But don't make it a thing, because then if we want a graph like that, we must just get out technology. In fact, I know some curriculum insist they actually draw S shapes here. Like, I don't know why, because why go to such level of detail? Because I don't know what's going on in between. It's kind of silly. In fact, if you want such detail, then be a citizen of the 21st century. Just sketch the thing with computer software. So be very judicious about what's important to teach, and it really is going to be the confidence to follow your nose and use common sense. What a gift to humanity that would be. Mathematics has excited humans, engaged humans, and motivated humans for thousands upon thousands of years. And it's not because humans as a whole love to do the odd numbered problems at the back of a textbook, or like to do worksheets in mathematics, or like to pass exams. There's something engagingly, inherently human about the mathematical experience. It's uplifting and delightful. So a lot of the curriculum, I wouldn't say, is uplifting and delightful, quite the opposite. So let's make it human. And let me give you one example. There's so much to say about that, but let me give you one example of making a typical piece of mathematics very, very human. Okay, let's do the algebra of quadratics. Here's a quadratic expression, ax squared plus bx plus c. Here's my very first human question. Quadratics. Quadratic, that's a very weird name. Quad, what does quad mean? Well, I know from my everyday language as being an English-speaking citizen, quad means the number 4. And I have to ask, right off the bat, what on earth does an expression like this have to do with the number 4? All right, ask questions about the jargon itself before we even do anything. Just ask questions. In fact, we live in the 21st century. Google it. Why do we call quadratics quadratic when quad means 4? And if you do that sort of research, you'll find something lovely here. The word quad here is actually referring to the Latin word quadratus. Quadratus means square. These became equations that could be solved by the method of the square, the quadratus method. And that's what's really going on here, because the whole topic of quadratics is really about the power of a square. So let me show you what I mean by that, because that's the human story behind this. The mathematics here is the power of the square. The symmetry of a square is our friend. So here are some typical textbook questions. By the way, let me point something out. It doesn't hurt to say the word please. Textbooks are so authoritative. Solve, blah, blah, blah. Solve, solve, solve. How about please solve, kindly solve? Would you mind solving? Let's be human about how we ask the questions too. All right, okay, here's 3 examples. Let's do this, not waste time. My first example is x squared equals 36. Let's solve that. And right off the bat, I don't know if you've noticed, I just said the word square. X squared. We actually use geometry words in algebra. X squared is referring to a square of side length x. There it is. Whoa. In fact, then there's a lovely human story here, because we also say something geometry about this one. X cubed. That's the side length of a cube. And x by x cubed. And then it becomes very curious, because we humans don't have a special word for this one. We just say x to the 4th power and x to the 5th power. Why not? Well, it's because we humans understand 2 dimensions, a 2-dimensional world. We understand 3 dimensions, 3-dimensional world is a cube. 4 dimensions, we have no idea what the 4th dimension is. We give up using geometry words for that. Very, very human. Anyway, my point is, we just used a geometry word for this very first example. X as a square equals 36. So the area of the square is 36. And the question is, what must that side length be? And we know right off the bat, x must be 6. It must be a 6 by 6 square. Now, if we go beyond geometry, we actually do know there's another arithmetical solution, which is going to name that x equals -6. Because -6 times -6 also equals 36, at least in arithmetic. So if we want to go beyond geometry, there's a second solution, the negative version, -6. Great, grand, and good. All right, part A done. Let's do part B. X plus 2 squared is 25. All right, I'm noticing I said the word square again. I said something squared is 25. I must be dealing with a square of area 25, and the something as a square has that area. Oh, my something is x plus 2. X plus 2 as a square has area 25. I know right away that x plus 2 must be 5. That's the geometry solution. If I give myself full arithmetic, I also know that -5 would also be a solution. Grand and good. Let me subtract 2 from everything. I get that x is either 3 or x is equal -7. Beautiful. X is 3 or x is -7. X is -7. Whoops, -7. Great, great, great. All right, feeling good. Until I look at that third one. And now I'm having an emotional reaction again, because it looks fundamentally different and it looks scary. X squared plus 6x plus 5 equals 60. Okay, deep breath. Well, I did say the word square again. I can at least draw an x squared piece. So there's an x squared term, which must come from x times x. There, I did something. That's great. But there's more. I need to add more to that picture. I need to add 6x to that picture. How can I add 6x to that picture? Well, I've got a side of x, length x here. What if I just do this? Excuse me. Add a length 6 there. That'll be area 6x. And great, I'll have x squared plus 6x. And then I'm going to hesitate because I'm nervous. Squares were my friend. I just drew something that's not symmetrical. I just drew a rectangle. I know what to do with rectangles. The symmetry of a square is my friend. Quadratics is about the story of squares. So what could I do to help make this more square-like? Now, it takes a moment of insight. Say, well, actually, split that 6x into 2 pieces. Make it area 3x and put the other piece underneath to make it a little more symmetrical, 3x. In which case, this is something times x is 3x, that must be 3. Something times x is 3x, that must be 3. Great. And now it seems absolutely compelling to complete the square. Literally complete the square. This must be, 3 by 3 must be 9 piece. People do not draw me pictures of completing the square in algebra books, most likely. But that's exactly what's going on. It's visual. It's visual. So I've got x squared. Bingo. I've got 6x. Bingo. I don't have 9. I've got 5. Oh no. What do I do? Well, if you want a 9 there, my advice is make it happen. Add a 4. Great. and deal with the consequences. If I'm going to add a 4 to the left-hand side, I better add a 4 to the right-hand side as well. So now I'm going to make this equation x squared plus 6x plus 9 equals 64. And the reason I like this piece, it's all these pieces right here. X plus 3 as a square is 64, and I'm good to go. Something squared is 64, so my something, my x plus 3 is either 8 or negative 8, and I can subtract 3 throughout. X must be 5 or negative 11 if I do basic arithmetic correctly, which I often don't. But there it is. Let's be very human in the curriculum. The story of quadratics is really about the power, the symmetry of a square. We are literally completing the square. Draw the pictures of squares. We're talking about them, actually do it. Be human about these wonderful things. All of mathematics is actually based on humanists, and we live in the 21st century. We can Google everything to find out what the story is behind it all. So do it. Let your students do it and talk about it.